If you have stood in the shadow of the Himalayas in the past decade, you've likely seen it shift. This region is undergoing a massive, irreversible transformation. From frequent disasters, unpredictable weather, and retreating glaciers, this roof of the world is creaking under the weight of a warming planet. What does this mean for the future of water, energy, geopolitics, and survival in the region? To answer this question, the Boring Climate Podcast is honored to welcome someone who has seen this change unfold with their own eyes. His insights have deepened our understanding of this fragile terrain, and it has never been more important than it is now to understand it better. Welcome to the show, sir. So to kind of set context for our listeners, you have been studying the Himalayan cryosphere for nearly 4 decades now. Why is it so important to study the Himalayan ice and snow, and what can we learn from it today in terms of how the climate is changing?
Thank you very much for inviting me to discuss the issue of cryosphere. And this is a very important area to study. Why this is important? Essentially because snow and ice is a solid form of water. So it actually melts during summertime and provides water to the various Indian river system. Since water is one of the fundamental elements on which life depends, therefore it is important for us to understand how snow is formed, how it melts, how glaciers are formed, and how the glaciers advance and retreat. So that is why it is essential for us to understand this landform, which is located at remote locations into the Himalayas. There are also, if you look into the practical terms, large Indian rivers such as Indus, Ganga, and Brahmaputra originates from these glaciers and seasonal snowfields. And since a Himalayan region receives larger snowfall and amount of water consumed by these rivers are not much, and that is why that water is get transported on the Indo-Gangetic plain, and it has helped to sustain Indian civilization for centuries. So in that sense, very important. It is also important because when the snowfall takes place, it takes place in winter. But that water is not available during winter time. It melts slowly during the summer. And when other sources of water is not available, then this water is available to the Indian river system. And because of that, all North Indian rivers are perennial. Otherwise, they are not like our peninsular rivers, which are seasonal in nature. But North Indian rivers are perennial, essentially because they receive water during summer because of snow and glacier melt. Therefore, it is very important for us to understand this Himalayan cryosphere so that we can sustain and manage our water resources for the benefit of Indian civilization.
Right, so before we get into the details of what you've been studying, could you tell us briefly how you got into this? Why did you start studying glaciers?
So, studying glacier and snow is definitely an accident, that I had just completed my master's program from Roorkee University and joined Indian Space Research Organization. So at that time, ISRO was a very exciting place to work because a remote sensing program and satellite remote sensing program was just started in India. So when I joined, India was about to launch its first satellite, which is a Bhaskara satellite. It was about to launch, and then ISRO decided that I should work on cryosphere. That was the idea because I was the youngest member in the team, and work was assigned to me to work on a Himalayan cryosphere, even though my expertise was on groundwater modeling. But it was, I also liked that idea essentially because from childhood I was excited to do the trekking. So I thought this is an opportunity to travel into the Himalayas. But what happened is, after completing some initial analysis of Bhaskara satellites, I got an opportunity to go to Canada on a Commonwealth Fellowship. And that is where I developed the academic background on Himalayan glacier. And when I returned back to India, I decided to continue to work on cryosphere, essentially because I was convinced that remote sensing has significantly can contribute into cryosphere studies, essentially because of two fundamental reasons. One fundamental reason is the snow and glaciers are located at very remote locations, and therefore it is very difficult to go and study there. But satellite can go periodically over there and provide us information. And most of these phenomena is on the surface. So these optical and near-infrared satellite images can really study those features quite nicely. Because of that, I thought this is an unique opportunity for us to develop remote sensing techniques for cryosphere series. That is how I got and I sustained for a very long period of time in this field.
Right, sir. Thank you. Actually, you brought me to the next question, which is so the Himalayas contain maybe the largest extent of glaciers outside the polar regions, but it's also really hard to access. And so you obviously saw some gap in what needs to be studied and how it is studied. What was that gap that you identified, and what were the models that you developed to address those gaps?
So I I remember my first expedition to the glaciers, because I was quite young at that time and excited and see the glaciers. So we have gone to the Chota Shigri Glacier expedition, which is organized by Departments of Science and Technology, and I was going onto the glacier there. And the basic idea of that time was to understand spectral reflectance of various features.
Okay.
The reflectance means that you have certain amount of energy coming from the sun. Part of that energy is absorbed by the object, like in this case it is snow glacier, and part is reflected. So whatever is reflected, by knowing its characteristic, we can clearly identify those features on satellite images. That was the idea. So I went there, I took the instrument, which was developed by ISRO, and we tried to study the spectral reflectance. So when we were having a first interaction with the all expedition members, there was one, there is expedition leader, Surendra Kumar. He was scientist in Wadia Institute of Himalayan Geology. During evening discussion, he raised a question that how many glaciers are there in Himalayas? So everybody was blank. That the second question he raised was how much is the aerial extent of glacier in Himalayas? Everybody was blank, because there was no answer. So the first question came in our mind at that time. Can we build a program to map Himalayan glaciers? So how do you do that? Because it is in remote location. Then there are issues related to mountain shadows. Then there are issues related to seasonal snow, that glaciers can covered by seasonal snow and they can be below. So you don't know how the glaciers are there. So that was the first gap I realized is we don't have basic information of Himalayan glaciers. So this year then we had discussed this issue, and then when I came back to Ahmedabad, I started to look into the satellite images, how to interpret it, so that we can get the aerial number of glaciers, its aerial extent, and other information. So I realized it is not easy to interpret. It's very difficult. So when next year I went into the glaciers, I decided to make a point that film it and take notes into the mountains. That is what all geographers does, So I was doing geography in McGill. So So first thing when said before I enter onto the glacier, I was sitting because you have moraines, correct? So moraines means is a rock transported by the glacier. So there is a ridge at the end. So I was sitting there and I was looking at the satellite images. I could not locate where because the certain portion of ice is covered by debris. So on satellite images, debris and adjacent area is the same. So I don't know up to what extent this glacier has come down.
Right.
So when I was sitting there, I observed that the river which is coming from the rocks is a place up to that extent glaciers are there, and you have ice. Then on top you have a rock, and below this river is coming out. So first clue I got is that the origin of stream could be a site, a place where we can mark the terminus. Huh? So that is how we started to build a program from the scratch. That sometime you have very clear spectral reflectors, and it is easier for you to mark the glaciers. But sometime you require to use these clues, and that clues are developed by your field observation. So the first gap was to identify this glacier extent in the Himalayas. So I developed this glacier inventory program. And in 1991, because my first expedition was 88 and 89, and 1991 I published first glacial inventory atlas of Indian Himalaya. So it was first time scientific community came to know that how many glaciers in Himalaya and what is the aerial extent. So at that time we said Indian Himalaya has around 25,000 square kilometer area.
Okay.
So it was that was the first major assignment I did, and it was developed. It's very important information and provided to the planning, and still it is considered as one of the basic work, and the database is still used by the scientific community.
And so you eventually, in 91, you answered the question, how many glaciers are there? How many were there then? Is the number the same? Does it change over time?
So number is very tricky business,
Yeah.
So it is not easy to find out number of glaciers,
Right.
essentially because it's very dynamic in nature. It's keep changing.
Correct.
Let us look into the Himalayas as a unit. You have Afghanistan to Pakistan to India, part of China, Nepal, Bhutan, Northeast India, and then, of course, part of Myanmar. So approximately we have 4 million square kilometer area into this entire Himalayan mountain range. So our study, which is basically carried out by Indian Space Research Organization, suggests that approximately 60,000 square kilometer area is covered by the glaciers. Now the question you ask me, that what is the number of glaciers? That is very difficult to say, essentially because glaciers advance and retreat. So once glacial retreat, each glacier is formed of number of tributary glaciers, right? So when the tributary glacier separates from main trunk, it becomes an independent glacier. So the number of glaciers keep on dynamic. So what happens is people ask question, how many glaciers are there? Sometimes you give number, like 10,000 number. Next inventory, it will say 11,000. So you say, number of glaciers gone up, though nothing is happening in mountain. But it is not like that. We should more stick to the aerial extent of the glaciated terrain, how it has changed over time.
Right. And it has obviously now, with a warming planet, the aerial extent of glaciers has reduced. Is that correct to assume?
That is correct. That is correct that Himalayan glaciers are retreating, and retreating very fast. And Because of that, there is a significant change in glacial areas taking place. But this rate of retreat is not constant throughout the mountain range. It is varying from place to place. Right. So if you take basins such as Satluj in India, in an average, glaciers are retreating around 15 meters per year. Some glaciers may retreat fast, some may retreat slow, but the mean retreat is around 15 meters. It is the same in Ganga and Ganga Basin, as well as it is similar in Brahmaputra. But in Indus Basin, River Basin, even though it is Satluj is a part of Indus, but if you go into the higher altitude, like Karakoram mountain range, glaciers are relatively stable. They are not retreating as much as we are experiencing in Satluj or Bias River Basin. So they are retreating, but they are retreating in a different rate in various parts of Himalayas.
Right. Right. So you spoke about the uncertainties of remote sensing and how it needs to be backed up by field visits. What are some of these uncertainties that came up over the course of your career, and what kind of field visits helped you, fill those gaps?
So one of the fundamental uncertainties is understanding the extent of glaciers. Correct. I was talking about how to mark this now, because at the end of the day, your retreat is a function of how you map terminus periodically, because you may have satellite data now from 1980 onwards, and then so around the last 45 years we have satellite data. How correctly we can mark the terminus will determine how correctly you estimate the retreat. Right, and then you have to transfer it on satellite on a map, and then do some analysis to understand how it is. So it is and then how many glaciers you can go into the mountains to do that. Going to mountain and going to terminus is very demanding task. I will give an example that around 1994, 95, maybe slightly late, we decided to go to Parvati Glacier, from where River Parvati originates, and Parvati is in Kulu district of Himachal Pradesh. To reach there, you required 4 days of trekking, right? So we were very fortunate to have very logistic support from Snow and Avalanche Study Establishment, which is DRDO establishment. So we went there. And first thing I realized, because by that time we had well-established team, and then we have detailed satellite images and everything. So we went into the mountains, and suddenly I found a huge cliff of ice. It was almost 30, 40 meters thick. That ice wall is there. I said, wow, now we reach to the terminus. Correct? So because ice wall is there, stream is also there, everything is there. When I saw the satellite picture, I realized, what is this? This is something. Terminus is supposed to be a few kilometers behind this, and we are still. Then we decided to camp there, right? Because by then evening has come, we camped there. Next day morning, we climbed that and went. Then we realized there is no glacier backside of this. It's only land is there. So likewise, 3, 4 this we went, and then we realized is that this thick ice wall is not a terminus, but it is called in term as a dead ice mounts. That means glaciers is retreating very fast backward, and it is leaving behind a huge chunk of ice, which is not melting that fast because it is covered by debris. So they are not attached with the main glacier body, but it remains as a ice body there, but it is not moving. Since it is not moving, it is not a glacier. So what will happen? So if you put that position as a terminus and you go for every year, you will realize glaciers are not retreating. Terminus is where. So if you look, and then there are a lot of papers which came later on which say that Parvati Glacier is not retreating because you have misinterpreted the terminus. But if you have satellite images, then you know that there is a definite terminus behind it and which is retreating. So one of the fastest retreating glaciers in Himalaya has been termed by some time as a non-retreating glacier. So that is why you need a combination of satellite images and field investigation to back up that observation. So that, but it takes huge time to do it, and because of that, every visit to mountain, along with satellite images, can bring a new understanding the way glaciers are behaving.
Right, sir. So another thing that we came across when we were looking at your work was something called the NDSI model, and you calibrated it specifically to the Himalayan conditions. Could you tell us more what is NDSI and what you did to calibrate it for us?
So NDSI means normalized difference snow index.
Okay.
So when this idea was started that we should monitor the seasonal snow cover. So these are two different aspects. One is a glacier and another one is a snow. Okay, glaciers is a mass of ice which is slowly moving down the valley. And the snow is an integral part of that glacial system. But seasonal snow is very different because it comes in winter and it melts in summertime and substantially land is clear. So what happens is, since snow falls in winter and melts in spring and summer, many Indian rivers get water from melting of seasonal snow. Therefore, it is necessary for us to map this. But geographical area is very large, correct? So we need an automatic technique to do that. We cannot do it manually. Like you imagine if you want to have a 4 million square kilometer area, we want to monitor it for snow cover. It is very demanding task. So we required automatic technique. So we decided to use this, develop a new technique which is called normalized difference snow index. It uses two bands because the solar radiation comes from sun. Some of that is absorbed and some of that reflected. So if you break down electromagnetic radiation into different spectral bands, you will realize that the visible band, which is a blue, green, and red, is reflected by snow. And if you take the near infrared band, which is around 1.1 micrometer, it is absorbed by snow. So if we have a satellite images on two different bands, one place it is reflected, another place it is absorbed, we can use this to develop an index to monitor snow cover. So, but there are a lot of issues in this when you are able to do that. First thing is to understand is what happens if it confuses with other features, whether it can confuse with vegetation, water, and then the satellite images are taken very early in the mornings, around 10 o'clock. So you have a shadow. So what happens below the shadow, whether we will meet. So all these issues has to be addressed. And we did extensive field investigation to understand how NDSI varies depending upon different features and what should be a threshold value above which we can consider it as a snow. So at that time, we thought zero point 0.4 is a threshold value. If NDSI is higher than zero point 0.4, it is a, you will know the how much is a seasonal snow cover. So it is one of the, that was a key development, essentially because we started to get first time idea about how much seasonal snow into the Himalaya, how it changes as it summer progresses, and up to what altitude it reaches at the end of summer. So that sense, this is first time information available to planners who are managing the water resources at Himalayan snow cover. So in that sense, it was very interesting and exciting.
Right, sir. So, another aspect of your work is glacial mass balance. Could you break that down for us?
What is mass balance? And so every year we have a snow which falls on the glaciers. And as summer comes, that snow melt. In addition to that, ice which is formed on the glacier, in the glacier, that also melts. So the difference between accumulation of snow and ablation or melting of snow and ice is known as mass balance.
Okay.
Why this is important? There are fundamentally 3-4 reasons why this is important. First important reason is it is very sensitive to climate. That means if there is a change in precipitation and if there is a change in temperature, mass balance can significantly change. Now, this mass balance determine retreat of glacier eventually.
Okay.
So, how much glaciers will retreat will depends upon long-term mass balance of the glacier. So, if you understand the health of glacier, you need to understand mass balance. Mass balance also tells us how much water is released by the glacier. So, if you want to do hydrological planning and other things, it is also important for us to understand mass balance. So, in that context, finding mass balance is very important thing in a glaciology. So, when I went to the first time to glacier in 1988, one of the things I noticed is it is very labor intensive technique because people were using the glaciological technique at that time. What glaciological technique does is you go into on the glacier, you put some stakes at various altitude and measure how much it has the depth has changed. You know how much it melted, and you go into the higher altitude, take the snow pit, and find out how much remains in this year. So you know, by knowing how much remains and how much is melted, you calculate the mass loss. But in order to do it, for one glacier, you required enormous team of people to work because going to glacier, staying there 10 days, 15 days is not easy thing. It requires a lot of support and other things. So at the end, you are going to have mass balance for only few glaciers because it is not possible for us to have it large number of glaciers because of financial constraints as well as constraint of trained manpower. So I was thinking we need to do something better than this because so at that time there was only few glaciers in entire Himalaya was monitored. So if you consider 9,000 glaciers are there in Himalaya, only 4-5 glaciers were monitored for mass balance. And then, unfortunately, people were interpreting that as if these are the representative of entire mountain range. And that has caused IPCC to say that Himalayan glaciers are going to vanish by by 2030. So I realized that we need to develop newer technique and better technique to do that. So we were talking about early 2000 now, right? Since then, techniques have also evolved. So around 2001, my first paper was published on using accumulation area ratio to estimate the mass balance. What is that accumulation area ratio technique is? The technique which I developed in here, which you have a winter time when the entire glacier is covered by snow. Then what happens is summer comes and snow is started to melt and the snow line is retreating upward. So snow line goes upward till the end of summer. Then what happens is again snow comes. So if you are able to monitor that snow line retreat by using satellite images, and where it reaches at the end of summer, we can call it as the equilibrium line, a snow line which is representing zero mass balance. And then how much area of glaciers remains above that equilibrium line, how much area remains below that time, take a ratio and then estimate a relationship between the mass balance and that ratio. And that ratio known as accumulation area ratio, and develop a relation. So whatever glaciers were studied at that time, around 10-15 glaciers were studied earlier by Geological Survey of India, then under our own program in Chota Shigri Glacier. We developed this relationship between the accumulation area and mass balance. And that is one of the pioneering work, is still quoted by the people. Even the paper was published around 2000, so almost 25 years back. So it provides very different opportunity to understand Himalayan glaciers, because first time we realized that mass loss is not constant throughout the Himalayas. It is varying. So traditionally, you go to the glacier, which is very near to road, because you want to go within a day to reach there. You are looking at the glacier, which is small in size, looking for glacier, which is not debris cover. All kinds of characteristics was used so that your life is simplified, right? So this is now, you can, all types of glacier, you can do it. And this has first time provided understanding of how is mass balance changing into the Himalaya, not for 1, 2, 10, but thousands of glaciers. So we launched, when I was in ISRO, we launched a major program to understand this, how mass loss is changing throughout the mountain range. And quickly we could say that nothing is going to happen till 2030, that glaciers are not going to vanish by 2030. So this is one of the interesting work which is provided insight into how Himalayan mass loss is changing. And there is an added advantage in this, because we can, since it is based upon temperature and precipitation, we can also predict how mass loss will change in future because of the climate change. Right. So this is now unique. This technique is now uniquely used to understand the impact of climate change on Himalayan glaciers also there. So I think this is one of the interesting work which we did.
Very interesting. So it becomes more and more significant now as the climate changes rapidly. But like you've been saying throughout, what is really important is how we interpret these findings, right? And it's easy for us to say climate change, warming planet, glaciers are, retreating, and it's all about climate change. But how much of this is caused by climate change and warming planet and human effects, and how much of this is a natural process that would have anyway happened?
First of all, we have to realize one thing is climate in Himalaya is changing. and changing it fast. So if you really analyze last 30, 40 years data about the change in temperature and precipitation in Himalayas, you will realize one thing is mountains are warming at much higher rate than global mean. So if what it means is if global mean rise is 1.5 degrees Celsius, in mountains it means 1.7 or 1.8 degrees Celsius, and that is known as elevated effect, which is now well established. So most of the Himalayan region where it warming is as high as around 2 degrees Celsius, 1.8 to 2 degrees Celsius. Second important thing has happened in mountains is change in precipitation pattern. That means now if you look into the snowfall data, you will realize there is no change in precipitation. I'm using term precipitation, which means rainfall and snowfall. Total amount is same, but rain component has gone up and snow component has come down. So there's a double problem for the Himalayan cryosphere. Right. Now, some of us are traveling into the mountains for last 40 years, and spend time. Now you go into the mountain, you will feel that mountain has changed very dramatically, and there are no reference points of past. And what has changed? See, I went to few years back. I was taking a pass, Kunzum Pass, and going into valley, Lahul Valley. I used to do that when I was young, very often, and after a long time, because I was going to various other. First thing I realized is graying of mountains. So what it means? It means that snow, because it depends upon when you are going into the mountains. If you are going winter time, everything is white, so there is no. As the glaciological, we go flag end of monsoon and early part of autumn, something around end of August or middle of August, we go and stay there till the middle of September. Suddenly I realized the mountains have become gray. What it means? It means that snow has really departed from large geographical area, and the rocks are exposed on the surface. Then snow line on the glaciers have significantly gone up. And the ice was there, which is covered with debris now. So debris cover on mountains have changed. Accumulation area, what we call where snow remains perennially throughout the year, has shrunk into the small, small pieces in very high altitude. So mountains are changing. There is no doubt about that. But that changes are not only in cryosphere region, that changes are there in downstream also, in the lower altitudes also. Because there are more people. Because see, I remember when we used to go to mountain in early 90s in Lahul Valley, you enter, you will not see people for months. Okay. But now it is quite crowded. There are a lot of roads, there are a lot of vehicles are going into it. Tourist infrastructure are dramatically changed, and defense establishment has aggressively moved into the mountains. So all these things are changing, right? So key question which you ask me is how much it is because of the anthropogenic origin and how much it is because of the natural changes. So the first, we have to keep in mind that the changes, the precipitation and temperature changes are happening because of the climate change, and which is a global phenomenon. Now, there should not be any misunderstanding with us that because it is one of the controversial topic in early 90s is glacial retreat is because of anthropogenic origin or not. But Earth history is a quite complex. So if you look into the Earth's history, particularly last couple of million years, you will realize the glaciers has always advances and retreated. So they call it glacial period and interglacial period. So people thought that present retreat is because of the interglacial period. And that is caused over millions of years. But now the changes which we are taking is so fast that which is happening within our own lifetime, within 10 years, 20 years, 30 years. So that has nothing to do with global phenomena of climate change. Global phenomena, I mean, is which is called Melanchthonic cycle. That means the way Earth is moving around the sun, there's a change in its characteristics, and because of that, sometimes glaciers are advanced in retreating. But recent models, climate models, clearly suggest that the warming has more to do with the way we are pumping carbon dioxide into the atmosphere, and there are other greenhouse gases also. So it is predominantly coming because of the human activities, anthropogenic activities, and anthropogenic origin. And so that we should keep in mind, keep that the present fast retreat of retreat is caused because of climate change. Now, climate change has two components. One component is caused because of global region, and one is caused because of the regional changes. So, global changes we have seen, we have put a lot of carbon dioxide. Regional changes, if you look into that, because we are developing significant infrastructure into the mountains, and it is leading to climate change into the mountain itself. Because I remember Spiti Valley, we have gone few years back. Before the COVID, 2018, we have gone, and we have taken the photograph of a glacier which was so bright and white in color. After last COVID, that means around 2023, we went there and we took the photograph. I realized it is completely become a black now. Why it has happened black? Because now adjacent there is a road and so many people are traveling, and it generates the dust and it deposits on the glacier, and it reduces its albedo, enhances its melting. So part of glacial retreat is related to the local climate change which we are doing. Another important thing is happening is as we are more and more traveling into the mountains, and at remote places also there are roads and everything, it changes because of road conditions are not very good, and it generates a lot of dust, and that dust gets deposited on the snow and it reduces the albedo. And remember one thing, once you reduce the albedo, it is an irreversible process. You cannot bring it back. See, pristine albedo has a 0.9 albedo. If it, because of the presence of dust on it, it comes down to 0.7, it can never come back to the 0.9 again, unless there is a fresh snowfall. Okay. So having said that, it enhances the rate of melting of snow. So now snow is departing relatively early than previous one. And what it means? It means now we have a huge gap between the departure of snow and arrival of monsoon. It makes mountainous terrain very dry. And it can lead to two things. Then mountain spring can die very early, or dry forest region can experience more forest fires. And if there is more forest fire, it means that you will have black carbon again generated from there, deposited in higher altitude, reducing its mass balance. So this is a feedback loop. I remember I had gone to Parvati Valley sometime in late February and early March, and there was forest fire. Can you imagine that? Clearly suggesting that mountain is changing, and it's changing because of human activity, enhanced human activity in the mountains, as well as because of the global climate change. So both are responsible.
Right. Thank you. So I don't think such a clear explanation has been given so far in understanding the impact. That is, it's very clear. We see a lot of news items also, even recently, about something called snow drought, where it's not snowing as much as it should be. These obviously have impacts on the people, on resources, on energy. And you've spoken about this as well. Could you elaborate a little bit on what this means for people living in the region as well as for, the rest of the country?
So it means a lot. Essentially, Bhar. So if you really look into the for the people which are living into the mountains, seasonal snow is very important for them. Essentially because um, seasonal snow is available at relatively low altitude, and what happens is it melts during springtime. You cannot have agriculture in mountain very early in winter time. You would have to have during springtime. It starts at summertime. If there is a shortage of water in summer, the agriculture is significantly get affected because of that. So whole idea of ice stupa came from there, that how to augment water inlet. So this is a very important thing. Another important thing is mountains are going to experience is as warming is increases, the agriculture, the regions which earlier used to have very nice apple orchards, now that will shift a little bit upward. So a change in agricultural pattern is likely to take place in future because of this thing. Now, if you look into the Himalayas, there are so many hydropower plants out there. Correct. So, but this is actually, as of now, this is a positive news for hydropower generation because since not glacier, seasonal snow is going to melt early in winter, so you have a more water available in winter, and that is where they have difficulty because in Himalayas, least water available in stream in winter time because rivers are frozen, right? So they get more water, so more it can be generated. But its impact is not felt in summer, essentially because now glaciers are melting more in summertime because snow is going early. That portion is picked up by glaciers. So amount of water is not reduced in summertime also. So it is a bonanza time for them. But this luxury is not going to last for long. Depending upon which part of Himalaya your hydropower plant is, this luxury is going to end by middle of century. Our model clearly suggests that, particularly in Satluj Basin, that this contribution for glaciers will go up till the middle of century and then it will suddenly collapse. So those changes are happening, and for some it is a positive, for some it is a negative. But it is more negative. So so that is how, but it can create a new risk and disaster for communities which are living into the mountains, and we are experiencing that now.
Right, right. Which brings me to the next question of the frequent disasters and floods hitting the region. You mentioned earlier that precipitation is remaining the same, but there's more rain and less snow. Is that one of the causes of these frequent floods in the region?
There are numerous reasons why this is happening into the mountain. So let us first understand one of the key difficulty in issue which you will face in mountain is heavy snowfall for a shorter period of time. Correct? And many times people call it as a cloud burst. Correct? So as temperature rises in the atmosphere, water holding capacity is also increases because warmer is the temperature, more moisture it can contain. And then what happens is mountains have a steep slopes and there is upward movement of wind. So more and more moisture is pumped into the higher and higher altitude, and because of warmer temperature, it can hold more water. So water, which is or vapor, which is available in air column, is relatively higher in mountain than on plains. That means when they fall very aggressively, and that is why we have cloud burst. So you are going to have a more and more problem of cloud burst in Himalaya. Now what happens? Now look into the cryosphere. What cryosphere is going to do? So when the glaciers move, glacier movement is not parallel with the surface. So if you have very high altitude, glaciers will come down. They have movement which is down, and as they come lower areas, its movement is upward. So it has a bottom, it creates erosion and creates the depression because of the movement of glacier ice. Once glaciers start retreating, that depression is filled with water. So what happens is you have now lake which is formed in the high altitude caused because of the retreat of glacier. Now when the water and ice interact, water albedo is very low. It absorbs energy and more energy transfer from water to ice, so it enhances the retreat of glaciers. Okay, so these lakes expand very fast. Now the lake which is formed is dammed because of moraines. What is moraine? The rock which is transported by glacier, which is a loose material. By any reason, it can collapse and create a massive flash flood in downstream. That is precisely has happened few years back in Sikkim. Right. Correct? Now we can add something more to this. What we can do is we can construct a hydropower plant on the stream, like what we did in Tista, at Chungtang. Correct? We had a hydropower plant, even though many people were saying it is too close to glacier. This water came, then your dam is also full, and it along with the dam water and this flush water, it has created a huge flash flood and taken all infrastructure, roads, everything along with that, right? So partly it is because of nature, partly because we have also our development activities has contributed and accelerated this disaster. Okay, so if 30 years back, if this had happened, there was no people, so you would not have felt. Now there are so many people are there, you instantly feel, right? That so many loss of whole hydropower plant has gone. That is a major loss. Then along with that, people have gone. So this is one thing. And remember, around 20 years back, 30 years back, you could map only 10, 15 glacier lakes in Himalaya. Now it is in thousands. And by the end of by middle of the century, it could be 10,000. So this problem is going to go accelerate in various ways. So we have to be very watchful the way we plan the development into the mountain. Second thing is what happens is another problem. What has happened in Rishiganga Valley few years back? You have now mountains on which you have a glacier ice, and over a period of time, glacier is formed because of very cold condition and because of the icing process. So it is a steep slope on which ice is there, which is we call it as a hanging glacier because it is now developed as a big glacier. Now you have a ice and you have a rock. They are attached with each other because of the frosting processes. And which is called the permafrost, permanently frost. That rock is permanently frosted and it is linked with that. Now, because of warming, that ice start melting. and it penetrates at the bottom, and this bondage is weakened. That frost becomes started to melt, and it creates a suddenly landslide or ice fall. That has precisely has happened in a Rishiganga Valley, and you have hydropower plant just to that it has vanished. So that is one thing can happen. Something more can also happen in mountain, right? What has happened in this year in Dharali, correct? So what happens now is glaciers have retreated and they have left behind the moraines, which is very loose material. And it has very steep slope and loose material. There is a cloud burst on it or rainfall on it. So this is a loose soil and rock which creates a slush instantly, and that slush comes down as a mud flow, and you can have a flash flood. That is what precisely can happen in Dharali. Something else can also happen in mountain, like what has happened in Kedarnath. You have a glacier with moraine, which is a huge chunk. There is, because of the heavy rain landslide, they blocks the small tributary, creates a temporary lake, and then it bursts and flash the flash flood. So many things can happen in mountain, right? Entire ecology is, or entire system is very fragile. So how you can handle this is, so there could be a, that is why we are experiencing now more disaster, and many things are happening simultaneously, like infrastructure is increasing into the mountain. More and more pilgrimages are going into the mountain. Climate change is taking place, cryosphere is changing. So we are all are experiencing this disaster very acutely because it is reaching to our homes now.
Right. Right, sir. Which brings me to a final question on policy in two ways. One is you earlier mentioned how the Karakoram ice is more stable compared to ice on the Indian, in the Indian Himalayas, and this is the basis of the Indus Water Treaty and water sharing between India and Pakistan. So, policy-wise, to understand the cryosphere and change policy or adapt policy, what are we doing well and what should we be doing better?
So let us first understand about the Indus Water Treaty. So Indus Water Treaty was written in 1960s. Nobody knew about glaciers, how many glaciers, where they are located, because I told you our first glacial and winter atlas came in 1990. So obviously they don't have idea about glaciers, how glaciers was extended, and technology and was not allowing them to do that at that time. So what Indus Treaty is, there are three basins allotted to exclusively to India, which is Satluj, Ravi, and Bias. Correct? So India can divert this water, utilize it fully. Remaining three, like Upper Indus, then Chenab, and Jhelum, is exclusively allotted to Pakistan with certain restriction to utilize in the Indian territories. But if we look into the glaciers in these two basins and the way, so it is, water is shared. So fundamentally, this treaty is very generous to Pakistan. Because if I remember correctly, only 20% of water is allotted to India and 80% was allotted to Pakistan. But in terms of cryosphere, if you realize, only 4-5% glaciated area is in these basins and 94-95% glaciated terrain in in a upper what they call is the Western River basin. And the mass loss of glaciers in river basin allotted to India is very high. And other region, it is very stable. So our model suggests that after middle of century, there will substantial reduction in eastern river basin, which is allotted to India, will take place because of retreating and vanishing glaciers. And at that time, Karakoram glaciers will start melting. Right now, they are not melting much, but they will melt after middle of century, and more water will be available. And this can affect the original quota allotted to the countries, because our quota will significantly reduce because of that. So this we need to address and probably renegotiate the treaty. But anyway, it is now suspended, so it is quite different ballgame now. But that is how original treaty itself was not very favorable to the Indian society in that sense. This is part of Indus Water Treaty. Yeah. But there are other changes are also going to take place, and which can enhance the difficulties, particularly the retreating glaciers. So what we should do about it? As I was discussing you earlier, there are a lot of issues which are coming in mountain. And some of these issues are related to formation of new lakes, then falling of hanging glacier, then very high snowfall, landslide caused from glaciated terrain, or potentially new lake where it can form because of landslide and other things. So scientifically, it is very difficult for us to predict all those things to improve the safety and security of people who are living into the mountains. So we should think in terms of how we have managed. So let us take coastal region, correct? We knew that coastal is very sensitive region and very fragile ecosystem. So we have a coastal regulation zone. Likewise, for us to think for mountain, whether we are going to have high mountain regulation zone. And what it means, it needs to be developed and it needs to be studied. This is a new idea we think we need to implement. Another issue on which we need to work is, until now, whenever we have a major infrastructure, we always do the environment assessment report. What is the environment assessment report means is, if we construct a major dam, how that major dam is going to affect the environment, the ecology, people living there, so many others. But in high altitude, this is not enough. We should also study, because of climate change, cryosphere is changing, and changing cryosphere will have effect on this infrastructure. So it is reverse idea. That means nature is changing and its impact on infrastructure. Right. So we call it is climate change impact assessment report. I think that should be also incorporated now to ensure that large infrastructure projects are sustained and we have sustainable development into the mountain. I think they are the two ideas on which we had a lot of discussions, and we are trying to say that we need to do it. I hope planners will really start looking into that and these issues.
Thanks. Right. Yeah. Thank you so much for this insightful conversation. It taught us a lot. And thank you so much for your time.
Thank you. Thank you very much. I appreciate for spreading this information to the larger community. Thank you.